Earlier, we talked about the term biodiversity and the idea that it encompasses a range of different attributes of species. From an ecosystem perspective, we like to think about biodiversity in terms of functional characteristics and the range and differences that we see in these functional characteristics among the species present in an ecosystem. In this section, we'll go over some of the basics of biodiversity and ecosystem function. Earth is currently in the midst of the 6th major extinction event in the history of life. If we take a look at the percentage of major vertebrate and vascular plant species that are currently threatened with extinction, birds over 10%, mammals up to 20%, fish approximately 5%, plants close to 10%. So that might not sound too bad. We're still going to have potentially 90% of the birds and 80% of the mammals, but the absence of some of these species might have disproportionate effects, and we don't necessarily know what the role of some of these plants, fish, mammals, or birds are in ecosystem function. These rates of extinction are 100-fold times higher than what it was before humans. The loss of these species may not have much of an impact, but it also might have a large impact. Diversity provides insurance against functional changes under extreme or novel conditions. So the presence of species with different functional traits gives us a certain kind of insurance that the main functions of ecosystems continue at similar levels, especially under extreme or novel conditions. Another way to think about this is that the presence of diversity stabilizes ecosystem processes over time. For example, diversity enhances the efficiency of resource use and retention in ecosystems. This is one of the first experiments to test the role of diversity in ecosystem functioning. And in the foreground, we have what was called the Big Biodiversity Experiment. Each one of these plots is somewhere on the order of 10 or 15 meters across. And they were planted to different plant communities. Some of these communities had a relatively low diversity of species, some of them just 1 species or 2 species, and others 16 or 32 different species were present. You can see just by looking at it, there's going to be differences in productivity associated with the species that are present. This one looks relatively productive, this one not quite so much, this one not at all. And these are probably some of the controls, the bare ground controls that you see. So the question is, what's going to happen over time? Will those plots that were planted to a high diversity of species have higher productivity, for example? And if so, why would that happen? Does the amount of productivity, if we were to take a look at the relationship between productivity and the number of species, what is that relationship going to look like? And this is NPP. Will it go like this? Will it level off relatively quickly? Or will it not necessarily saturate so that each additional species increases the amount of productivity that we have? This is a more recent picture, and this is one that was taken in the fall after the plots had developed a lot more. And you can see really big differences in the types of species that are there and the diversity of species. So which plots had the greatest productivity? And why would that occur? Well, one of the ideas that is tested in this experiment is the idea of complementarity. So how similar or how different are different species? And if we were to take a look at differences in functions for species, one species might have a set of functions like this, and another species a set of functions like that. Does the presence of having both of those species present in a plot have a large impact on the ecosystem function, or is just having one of those species enough? When we think about complementarity, the question of what functions are most important rises to the top. And we need to think about different types of resources that plants use, but also their rooting depths or seasons that they absorb nutrients. The phenology of species is important when they're active during the growing season, as well as some of the traits that they have, differences between, for example, C3 versus C4 photosynthesis. All of that comes into play when we're thinking about how diversity impacts ecosystem function. These are the results from that experiment, at least relatively early on. On the x-axis, we have species richness. On the y-axis, in this first panel, we have total plant cover, and that should be 45. So total plant cover is on the y-axis, and that's basically how much of that space is going to have plants in it. And it's an index of productivity. What we can see is that we don't get a curve that looks like that, nor do we get a curve that's flat, or one that levels off. It's a saturating response, but it hasn't necessarily saturated at even 25, or in this case probably 24, different species. The addition, on average, of more and more species leads to greater total plant cover. So whatever the differences are of the 4th or the 5th or the 10th or the 24th species, it still leads to a marginal increase in how much of that ground is covered. In addition, when we take a look at another index of ecosystem functioning, how much nitrate is present in the rooting zone, we can see that the addition of species leads to lower and lower nitrate concentrations. So having more species is going to better utilize the nitrogen supply and leave less of the nitrogen available in the soil. And that might be a cause of this pattern that we see in total plant cover, or simply a consequence of having more species that are present. Either way, we see a similar type of relationship where the addition of additional species still leads to increases in cover and declines in nitrate availability.